So we are embarked in the search for life beyond Earth, and that's our field of study. And I will be giving you sort of an overview of this endeavor, and then our good friend and colleague from NASA, Carol Stoker, will be giving you a little bit more specific information in her particular areas of research. So since it is after lunch, and I know this is a difficult time, I do want to say if anybody falls asleep during my talk, you will be visited by an alien tonight. You will be taken away to another planet, so just in case. All right, let's proceed. So we're going to talk about the search for life and intelligence beyond Earth today, and we're going to, okay, we're going to talk about how it works, where it stands, and why it matters. There we go. Yeah, I guess I have to. Okay, so there are three major science questions that we are involved in our pursuit, and these are questions of space science and space exploration. The first one is, how does the universe work? And that has to do with cosmology, astrophysics, big questions like the formation of galaxies, the Big Bang, the start of everything that we know about our universe, stars and planets and life. So how does the universe work? The second question is, how did we get here? So what were the processes and conditions necessary for life that led to life emerging on planet Earth? How did life begin? And then, are we alone, is the third question, and that's the conditions that led to life on Earth, do they exist elsewhere? If so, might we have the capabilities to look for them and find them and characterize them? So those are the big questions. What's interesting is these aren't our questions. These aren't general questions of science. These are NASA's top 3 science questions. So these are the priorities of NASA's space exploration, to answer these questions. What's interesting is the questions that we're trying to answer have changed from questions that have previously been relegated to philosophy and science fiction into the world and domain of science fact and actual research. So for the first time in our history, we actually have the tools and technologies to answer these questions. So the SETI Institute, our mission is to lead humanity's quest to understand the origins and the prevalence of life and intelligence in the universe, and then also share that work with the world. And our organization has the Carl Sagan Center for Research, which is for scientific exploration and study. It has the Center for Education, where we do education programs to engage and inspire what we hope are the next generation of researchers. And then we have the Center for Outreach, which engages and interacts with the public to inform of what we're doing. So our team is men and women from all over the world, different cultures and backgrounds, and different scientific backgrounds as well, but they combine together to undertake the science and mission of the Institute. And it's a very diverse and wonderful group of scientists, educators, and professional staff. So some interesting facts and figures about the Institute. We were founded in 1984, so this is our 40th anniversary this year. We will have a big party in November. If you would like to go, please get in touch with us, but it'll be fun. Jill Tarter, who's a very famous pioneering radio astronomer, she's now turned 80 years old. She decided to have a career in radio astronomy at a time when women weren't even allowed in observatories. So this is the kind of pioneering spirit that Jill brought to our institute. We have more than 90 PhD research scientists and 55 research affiliates. We've got at least 20 separate fields of study or scientific backgrounds that our scientists represent. We have 10 professional staff who focus on education and outreach and also communications. So we've got 130, actually now 135 staff in total, and our headquarters are right down the street here in Mountain View, California, beside NASA Ames. At any given time, we've got about $120 million in active funded research programs ongoing at the Institute. There's usually about 150 different kinds of research projects happening at any given time at the Institute. Much of our funding comes from federal grants and research contracts. We apply for those, and sometimes we win and sometimes we don't, depending on what kind of science we proposed and the interest of the funding agencies. And then the balance is donations. You talked about a 501c3. We are also a nonprofit research institution, so people do donate money to help us do some of the research that federal grants don't cover. So we, among other things, serve as a private contractor to NASA for something called planetary protection, which is about protecting the worlds we plan to go and visit or have visited, and also protecting ourselves if we're bringing samples back from these environments to make sure there's nothing dangerous or problematic. We also oversee an applied artificial intelligence and machine learning program called the Frontier Development Lab, where we apply these new data analytic techniques to interesting science questions in partnership with NASA and the US Department of Energy. And that's a program, if you're getting a doctoral degree in the process or have one recently, you can participate in this program. Again, we bring together computer scientists and different scientists in the natural fields of science together for these programs. We own and operate the Hat Creek Radio Observatory and what's called the Allen Telescope Array, which is part of which is seen in this picture here in Northern California. We also run a project called Cosmic on the Very Large Array. This is the big set of dishes in New Mexico. And if you've ever seen the movie Contact, there's a movie poster with Matthew McConaughey and Jodie Foster, and behind them are the dishes of the Very Large Array. So that's currently the biggest and most ambitious SETI program in human history operating on that instrument at the moment. I'll say more about it later. We also manage and administer education programs in partnership with NASA and the National Science Foundation. And we develop formal and informal curriculum materials for young learners and learners of all ages for our education programs. And a lot of our work is also done with public talks, a radio program and podcast and lectures where we bring our science and stories to the general public. So we have a lot of interesting characters at the Institute for our history. Jill Tarter, our founder, Frank Drake, famous for the Drake equation, which we'll also talk about in a moment. Baruch Blumberg and Charles Towns are two Nobel laureates, one in physics for inventing the laser, one in medicine for his work in hepatitis. Carl Sagan was a famous scientist and astronomer here in the US who popularized astronomy and astrophysics when I was a young person, and he was on our board as well. Lou Platt was formerly one of the CEOs of Hewlett-Packard. David Newman runs the Media Lab at MIT in Massachusetts and was also the deputy administrator at NASA during the Obama administration. John Gianandrea heads up AI for Apple. Avery Wang invented the Shazam app. How many have the Shazam app on your phone, which can tell you what music you're listening to if you just hold it up to a speaker? That's Avery. Minnie Wadwa is the head of planetary neuroscience at the University of Arizona. Brother Guy is the Vatican astronomer, so he reports to the Pope, and he is the Vatican's astronomer. He's also on our science advisory board. David Grinspoon, who now is in charge of astrobiology at NASA, was on our board before he took that position at NASA. So a lot of interesting key personalities, past and present, at the Institute. So we'll talk briefly about how this works and the three methods that there are to look for life in the universe. So the first one is in situ instruments. In situ means in place. That means you send hardware to the place you want to study. You put in a rover or a lander, and there you can then use those instruments to characterize that environment or do other things like look for life or signs of life, past or present. Then there's remote sensing, where you're observing from a distance using telescopes or orbiting platforms. They can be optical, like a telescope, or doing spectroscopy, like the James Webb can be. So these are just different techniques. And then there's SETI observations, where we can look for signs of technology, like laser pulses or narrowband radio signals that can come from across the galaxy or even outside the galaxy and give us the opportunity to find them. So these are the three main methods that we use to look for life in the universe. So again, in situ or in place means sending the technology to the place of interest. Remote sensing means studying different environments and places from a distance. James Webb Space Telescope, by the way, has the ability to look at the atmosphere of planets around other stars and characterize the environment of those atmospheres. What's in those atmospheres? Is there oxygen? Is there water? Is there nitrogen? Is there methane? And so forth. So an extraordinarily capable telescope that is doing much more than just doing observational astronomy. And again, this is an important remote sensing capability. And then, as mentioned, SETI technology using ground-based instruments to look for what we call technosignatures, or signs of technology from beyond our solar system that would suggest the presence of life and intelligence. It's a big universe out there. So this is our solar system, and in it we have 8 planets, we have 5 minor planets, we have 280 odd moons, we have over 3,000 known comets, we have 1 million asteroids. So there's a lot of material in our solar system, and it's pretty big. If you were traveling at the speed of light, it would take you 5.5 hours going that fast just to get to Pluto, which is the little planet at the edge of our solar system. And if you were a rocket made by humans, called the New Horizons mission, it would take you 9 years to get there, traveling at 56,000 kilometers per hour. The fastest object ever made by humans took 9 years to get to Pluto. And it gave us the wonderful images of Pluto you may have seen in the news back in 2015 when it crossed there. In terms of scaling the search, our solar system is just this tiny little collection of planets at the edge of an ordinary galaxy, looking sort of like this, which is a collection of hundreds of billions of stars. So we would be sort of an insignificant, invisible object at this scale. So this is 100,000 light years across. So it would take a photon of light traveling at the speed of light. We think of that as instantaneous. You turn a switch on and the lights go on. It would take 100,000 years for a photon of light to cross from one end of this galaxy to the other. And this is just one of hundreds of billions of other galaxies in our universe. And what's interesting is what we now know, and I'll tell you how we know this, is that in this galaxy alone, in our galaxy, the Milky Way galaxy, we estimate there to be tens of billions of potentially habitable worlds or planets. And this is fairly new knowledge. There was a gentleman named Frank Drake, I spoke of him earlier. He did develop something called the Drake equation. And if you Google that, you'll see lots of information about it. It's quite famous, not as much as E equals MC squared, but pretty popular. And he used this, he was trying to develop a framework to answer the question, well, how many technological civilizations might there be in our galaxy? How would you even go about estimating something like that? Well, he said you need to ask a bunch of questions. One of the questions you need to ask is, what is the birth rate and life cycle of a star? I mean, stars are sort of fundamental. It's the source of energy in our solar system. And we didn't know it at the time. We now know that stars are the birthplace of planets as well. So, but how many stars have planets? In 1961, when he did this work, we didn't know of any planets beyond our own solar system. And then if there are planets, how many of them might be habitable or Earth-like environments that could potentially harbor life? And if there are some of those, how many actually do develop life? And in how many cases does intelligence emerge? And if intelligence emerges, in how many cases does technology arise? And if that happens, how long does a technological civilization remain detectable before something else might happen? So these were the questions, and he put them together in a formula because he said, actually, I can express these as a formula or a relationship where the product or the multiplication of all of these factors would give us some estimate of technological civilization. So the number of technological civilizations would be a function of stars, planets, habitable worlds, life, intelligence, technology, and how long those civilizations last. So we have a structured approach for research at the Institute where we have one question. The question we're trying to answer is, are we alone? We have 3 different domains of research where we investigate that question: the structure of the universe, planets and habitability, life, complexity, and intelligence. And then we investigate those through 6 divisions of research at the Institute: astrophysics, exoplanets, which are planets beyond our solar system, planets orbiting other stars, planetary exploration, astrobiology, climate and geoscience, and radio and optical studies. So these are all the kinds of research that we undertake at the Institute. So what we do is we do research across the natural sciences. We support NASA missions. We do field expeditions all over the world. We do laboratory research. We do astronomy, both in the optical and the radio domain, using both ground-based instruments and space-based instruments. We do technology and instrumentation development. We have an instrument on the Curiosity rover, for example, which analyzes the soil on the surface of the planet and tells us what it's made of. So we also, in our efforts, we're trying to understand the structure of the universe, planetary environments and habitability, the nature and origins of life, and the evolution of intelligence and technology. So a day at the office for us is, supporting missions like KSEA or TESS or Curiosity or Perseverance on Mars, or New Horizons, that's the one that flew past Pluto, or we're using radio telescopes like the VLA in New Mexico, or we are in the field in the Atacama Desert or the Antarctic or the high Andes of Chile. So our work takes us near and far. The SETI programs we have at the Institute are, again, our Allen Telescope Array, which is the world's first and only radio telescope array purposely designed and built for searching for extraterrestrial intelligence, very, very faint signals. It's designed to look for a needle in the haystack. And also the very large array in New Mexico, where we, again, have a project called COSMIC, And in this particular location, we are bringing data, astronomical data, into that radio telescope at the rate of 3 terabytes per second. So it's extraordinarily huge amounts of data. And then we have Laser SETI, which is a global project distributing camera systems like this that might look for laser pulses, also as an indication of technology and therefore intelligence and life beyond our solar system. We do work all over the world in terms of both field expeditions, where we're doing science in the field to figure out how to do science in other locations, including how to design and build rovers, what instruments they might need, and so forth. But also these locations indicate where we have radio telescope systems, optical telescope systems, and partnerships. So it's a global effort that happens worldwide. And then there's this subset of field called astrobiology, which broadly is about the search for life in the universe of any kind, even from microbial life, which could still be found in our own solar system. And there are 3 primary questions there. How does life begin and evolve? Does life exist elsewhere in the universe? What is the future of technological life? What is our future? There's a good question in that, what is our future, with some of the challenging things that are a result of our own technologies, like climate change and so forth, that give rise to these questions. So astrobiology studies origins, evolution, distribution of life, and it hopefully helps us also recognize biospheres or environments where life might exist that could be nevertheless very different than our own. What's also interesting here is that, again, we're involved in all of these branches of science: chemistry, physics, biology, astronomy, geology, climate science, planetary science. These are all human inventions, right? Nature is not divided into these categories. We divide nature into these categories so we can take a deep dive and study them. But in reality, these are all part of a very complex system and a complex set of processes that work together to result in us and me here giving this talk right now. So I call it connecting the dots, and this is what multidisciplinary science like astrobiology, astronomy and astrophysics, and SETI endeavors try to do, is connect the dots between these disciplines and understand how the whole system works. So what have we learned so far? Where does the program stand now? Well, one of the things that's interesting is, what do you see in this picture? Anybody?
Star.
Stars. Anybody else? No, it's a star. So yeah, you can see the Milky Way galaxy here. But actually, so what I'd like to say at this point, if you said stars, you're wrong, but thank you for playing. These are not stars, of course, they are stars. But in fact, what they are solar systems. Statistically, what we know now is that every star in the sky has 1 or more planets around it. And we didn't know that more than 15 years ago. So we have what I now call a new Copernican revolution, and was really in many ways started by these 2 gentlemen, Didier Queloz and Michel Mayor, who won the Nobel Prize in Physics in 2019 for discovering the first planets beyond Earth, so-called exoplanets. These were big Jupiter-sized planets. And then a gentleman named Bill Barucki from NASA Ames, right down the street, said to NASA, I want to build a telescope that can look for more planets, and maybe Earth-like planets. And NASA said, it can't be done. He tried 4 times, and they said, no, it can't be done. And then he tried a 5th time, and they said, okay, let's try it. So they built an instrument called the Kepler Space Telescope. Not many people have even heard of this mission. I think it's the most profound mission NASA has ever launched, because it forever changed our perspective of our place in the universe and our place in the cosmos. So the Kepler mission worked by staring at hundreds of thousands of stars at the same time and looking for the possibility that if they have a planet, that planet might pass in front of the star. And if you're looking at how bright the star is, the light would dim just a little bit. And if that happened on a regular basis, you'd say, there must be something causing that. Could be a planet. Well, it found thousands of planets. Of course, it didn't see stars that size. It saw them as tiny little dots of light. So it was an amazingly sensitive instrument that it was capable of measuring these so-called light curves or dips that were the result of planets. But it really changed everything we know about our universe and the cosmos. This is what we knew about planets before Kepler. So as a result of the work of Queloz and Mayor in the 1990s, we had found a bunch of planets, or like big ones like Jupiter and Neptune. These are all planet size, big, medium, Earth size, smaller. And so it found lots of them. Then we launched Kepler. That changed everything. So all the yellow dots are planets found by Kepler. And if you look at them now, you see these are smaller and closer to Earth-sized planets, because this technique was able to find these smaller planets, whereas the other technique is not able to find these smaller planets. So doing the math, because it's a very unusual event to have an orbit right in our line of sight if we're happening to be looking at a star. So you do the math backwards, and the conclusion is every single star in the sky has one or more planets. So this is an extraordinary new discovery. And so the Kepler mission taught us that every star in the sky has one or more planets. The majority of planets fall between like Earth or Mars and Neptune in size, kind of Earth size. And that approximately 20%, some people have said as high as 50%, but between 20 and 50% of them are like rocky, small, right-sized worlds and the right distance from their star where they could potentially support things like liquid water and have the conditions necessary for life. So that means tens of billions of potentially habitable planets just in our galaxy alone. So that's kind of exciting news, at least I think so. How much do we now know then? So if we look back at the Drake equation, actually we knew about the birth rate of stars in 1961 when he put this together. That's the only thing we knew at that time. But since then, thanks to the Kepler mission, we know that all the stars have planets. And we also know that a good percentage of them are habitable environments. What we don't know is how many go on to develop life, intelligence, technology, and duration. So that's still a question, which I also call job security. It's very important. So if we answer those questions, I'm out of work. Okay, so, but what is the impact and why does it matter? So there's supposed to be a video here. Because the sound quality isn't so good, I'll skip over this, but I would urge you to go to our website at SETI.org, and if you scroll down from the home page, you can see that the video, it has a very famous person's voice telling a very short story. So I will skip over it, but urge you to take a look later. It's really quite fun and interesting. But so what is the future of life on Earth and beyond? And you know, it starts here on Earth. What we learn about possible alien coevolutions allows us to better understand life and habitability right here on our own planet, and also to identify habitability thresholds that we should not cross. In other words, our world is an island, and it's a habitable environment, but what makes it habitable is a very fine balance of conditions that we don't want to mess up. So this kind of work, as much as we think this is about looking at worlds beyond our own solar system, it's also teaching us a lot about our own world and about ourselves. So it teaches us to develop a responsible approach to our own environment as a civilization on Earth, and perhaps also prepare us to become an interplanetary species. And it extends far beyond, because also it helps us understand the future of life as a process in a changing universe, because that's the other thing that we know, is the universe is a dynamic, ever-changing place. It's not a static place. And it's also about what it means to be human. So it sparks our curiosity, this kind of work. And curiosity is what unites us all as humans, as a species. Everybody on this planet, as a human being, is a curious character and a curious member of the species. That's what unites us all. We all have this trait in common. Also ignites a sense of wonder. So this brings us, these quests bring us, you know, right face to face with just how big the universe and how vast it is. And we're really pursuing some of the most profound questions in science, because to make these discoveries would really be transformative moments in human history. And ultimately, it's also about human nature, because we're social beings, right? We don't necessarily want to be alone. That's why I think the public is fascinated by things like UFOs and aliens and so forth, because the idea that in this vast universe we're the only place where an intelligent species and technical species exist would be a pretty scary thought. So it's about inspiration, excitement, and hope. Just to give you an idea, there's all of these wonderful pictures of different objects. And I ask people, you know, what do these have in common? And then people are trying to think about the scientific answer. And it's not a scientific answer. What they all have in common is these were pictures on the front page of the New York Times. Why? Because they were about interesting stories. And so these are the kinds of stories that, in spite of all kinds of other strife and politics and war that appears in the newspaper sometimes, these kind of inspiring stories are there too. And they give us new knowledge and understanding and take us to different places. So we also like to leverage this fascination that the public has and leverage awe in education programs like NASA Astronomy Ambassadors, education program for community colleges, which are a very important bridge to underrepresented communities in the United States, programs for young learners like Reaching for the Stars, and another NASA-funded program which was for the Girl Scouts, which we're now planning to deploy internationally. And we also have every summer, as do our friends at NASA Ames, a research experience for undergraduate internships, which is a marvelous program. So you can get to know us, you can get involved with us, and it all starts there. If you go to our website, you can learn more about what we do. And your friend and colleague Joan Yee is a scientist with the SETI Institute, and I'm sure would also be happy to tell you more about it. Some of your colleagues here also visited our offices on Tuesday. So we welcome you, and very happy to be here and make new friends, and thank you very much for your attention.